Hi, my name is Ron Rodriguez, and I'm a student in the ILS program in ENEL 327 in winter 2023. I'm going to be talking to you about time frequency analysis, the Gabor Transform, and filtering applications. We're going to go over the motivation for time frequency analysis, talk about the short time Fourier transform, window functions, the Gabor transform and its inverse transform. We'll go through a filtering example, and then we'll go through some conclusions. So music and other interesting signals, including speech, change their frequency content over time. Sometimes it's important to identify when an event of a certain frequency has occurred, not just that the frequency was present in the mix. Spectrograms are used to visualize the frequency content evolution of a song over time and can be used to fingerprint certain types of sounds. And this can be used for machine learning recognition of dog barks, human speech, and for creating time-variant impulse responses. So this is a picture of a spectrogram, and we can see on the y-axis we have frequency, and on the x-axis we have time, and we see that the frequencies are changing at every time, but we can pick up some dominant frequencies that's at certain frequencies representing various things. This is the time frequency plot of someone vocally saying 19th century. So the short time Fourier transform is an extension of the Fourier transform that uses a window function, which is usually a pulse or a Gaussian bump, as a small bandpass filter that focuses on a certain region of the signal in time. This region is then Fourier transformed into the frequency domain using the DFT, and the window is slid along the entire extent of the time domain signal to the next spot, and the process is repeated. Collecting each of these frequency domain time series, we will produce the time frequency spectrum. Mathematically, the short time Fourier transform is given as the integral from minus infinity to infinity of the function times the window function, so the signal times the window function at time tau, and multiplied by the complex exponential sinusoid. The inverse function, the inverse short time Fourier transform, brings the time frequency spectrum and inverse Fourier transforms it back into the window. Now, it turns out that for certain choices of windows, there will exist a way to invert the function back to f of t, and for other choices of window function, the Fourier transform or the frequency domain representations of the time frequency plot will not be invertible. So there are several choices of window functions that are possible, but some of these choices will make the short time Fourier transform non-invertible. A couple examples are the pulse, which is given by u of t minus tau, and a Gaussian window, or a bump function, e to the minus pi t minus tau squared. So this particular choice of window function is used in what is called the Gabor transform. So using the Gaussian window function in the short time Fourier transform gives us an invertible time frequency representation called the Gabor transform, which is in time and frequency. And we have a window function at time slid to centralized around time tau, so that the center of the bump is at time tau, and it's multiplied by the function, which zeroes out all of the values outside of the window and preserves the function values within the window scaled by the Gaussian, and then multiplied by the complex exponential, e to the minus j2 pi ft dt, and we integrate from minus to infinity. So this takes one window and sends it in at a centralized at a time tau and sends it to its frequency spectrum. To get the inverse, we take the inverse transform of the frequency spectrum of that window of the function, transform it back to time domain, and then sum up all of the different time domain inverse transforms. So we take the particular frequency spectra, invert it, and that'll give us one window of the signal in time domain, and then we add that to all the other additional windows that and that will give back reconstruct the original signal x of t. Now the Gaussian window focuses the signal to time centered about the offset of the window, and then this sample is transformed to frequency domain in the discrete case using the fast Fourier transform, and then the inverse transform performs the IFFT, the inverse fast Fourier transform, on each column of the output, and then sums these together to reconstruct the original signal. So now we're going to go through a frequency filtering example. We take a 10 hertz low amplitude signal and we will embed it into a noise signal. So we're taking sine 0.5 sine 20 pi t u of t minus 3, which is this signal here, and then we're adding 30 sine of pi t squared to it. And so this signal, that is the important message signal with some kind of important digital encoding that we're trying to receive or transmit, is being overprinted by a louder, higher amplitude noise signal, which could be represented by someone transmitting a radio signal and then someone jamming the signal with a louder broadcast signal. When we Fourier transform the original signal, we get a spike in amplitude at 10 hertz, and we also see a change or an increase in the phase at 10 hertz. When we look at the signal buried in the noise, we see a bunch of different frequencies, although we can make out a little spike there at 10 hertz. And then we also see some ramp up behavior in the phase spectra, which could give us a clue that there's something going on at 10 hertz, but it's not clear. So what we're going to do is we're going to multiply the noise signal by a window, by the Gaussian window, and that this produces a windowed version of the function. And we take this time domain windowed function and send it by the FFT into frequency domain and look at its spectra. And this will make one column of the time frequency plot centralized at time tau, which in this case is tau equals 5 seconds. Then this window will slide along the entire length of the signal to produce various windowed versions of the signal, which will create the time frequency plot when you transform it into frequency domain using the FFT. So this is the Gabor transform, and this will allow us to filter out noise. So when we Fourier transform it, we get this spectra, and this will produce a single column. This entire thing here in magnitude is the column, the vertical column in the time frequency plot at time equals 5 seconds. So here we have frequency on the x-axis and time on, or frequency on the y-axis, time on the x-axis. And then as this window slides, it produces and is centralized at the next time increment, it'll produce another column of frequency spectra data. There we see the sweep, the noise sweep, sine 30 sine pi t squared. And then if we look closely, we'll see a faint signal at 10 hertz. So to recover the signal, we will try to do some filtering. So one way that we can filter is to cut everything above, slightly above 10 hertz. And we see that wipes out, we zero out all the data above 10 hertz. We could also, since we know the signal started at 3 seconds, we could also zero out everything below 3 seconds. But basically we take the time frequency spectra and we do a filter, we apply a filter, and then we inverse Gabor transform this using the inverse transform. And what we get back is this time domain representation here, where we see that everything after about 6 seconds, all the noise has been removed. And we can clearly make out the message signal with the important digital information that we're trying to transmit or receive. And so this could be filtered further, either in frequency domain or in time frequency domain, and then inverse transform. So here we're forward transforming it to look at the spectra. We see that noise has been wiped out above 10 hertz. And we could also do some additional work to clean this up using filtering. So in conclusion, time frequency representations of time domain signals offer a useful analysis tool for signal detection and for filtering. The short time Fourier transform is a straightforward extension of the regular Fourier transform, and using a window function to limit the extent of the signal under analysis. And the Gabor transform provides an invertible transform that is implementable in software packages such as MATLAB and can be used for time frequency filtering. And filtering is performed in both frequency domain and in time frequency domain, which can uncover low power signals out of noise. For instance, a GPS signal coming from a satellite that's being jammed. So the references used in this work are the Cruise MATLAB Toolbox, which is available at this link, and a paper by Dr. Gary Margrave and Dr. Michael Amaro from the Geophysics and Math Department of the University of Calgary. Thank you for your time and attention.